Hi, it's Tim. What happens when we ask mathematics to evaluate something that, by definition, does not exist? If we attempt to divide a number by 0, the system breaks down, and we are left with an undefined void. But what if both the numerator and the denominator vanish simultaneously? What happens when we face the absolute paradox of 0 divided by 0? On one hand, any fraction with 0 on top should be 0, but on the other hand, any fraction with 0 on the bottom should blow up to infinity. So which one is true? This is not a failure of mathematics, but rather the exact edge where calculus begins. To understand this landscape, we have to look past what happens at a single point and explore what happens as we get infinitely close to it. This brings us to the foundational concept of the limit. So let's look at a concrete function to see this tension in action. Let's write down a function f of x equals x minus 1 divided by x squared minus 1. Now, if we try to evaluate this function directly at x equals 1, we run into a immediate wall. The numerator becomes 1 minus 1, which is equal to 0, and the denominator becomes 1 squared minus 1, which is also equal to 0. We're completely stuck if we only look at that single instant. But notice what happens if we look at a neighborhood surrounding x equals 1. If we choose an x value slightly less than 1, say 0.99, and plug it in, our output is roughly 0.5025. If we move closer, say 0.999, we get 0.5003. On the other side, if we approach from values greater than 1, like 1.01, the output is 0.4975. And if we step even closer at 1.001, we find ourselves at 0.4998. Therefore, even though the function is completely hollow at x equals 1, the behavior around it is perfectly predictable and elegant. The values are tracking directly towards 0.5. And this brings us to our intuitive definition of a limit. We write that the limit as x approaches a of f of x is equal to L. What this means, quite simply, is that we can force the values of f of x to be as close to L as we want, purely by restricting x to be sufficiently close to a without ever letting x actually equal a. Now, for the example we just looked at, it didn't matter whether we approached from the left or from the right. The journey led to the exact same destination. But on the other hand, many functions describe systems that experience sudden jumps or breaks. Think of a light switch being flipped or a sudden change in physical state. To handle these systems rigorously, we need a concept of directional or one-sided limits. Let's illustrate this by drawing a piecewise function on our screen. Let's define a function g of x such that it is equal to x plus 1 whenever x is less than 2, but it instantly drops down to equal 1 when x is greater than or equal to 2. Let's track our path as we travel along the curve towards x equals 2. If we come from the left side, meaning we're looking only at values of x less than 2, we're walking up the line x plus 1. As x gets closer and closer to 2, our altitude climbs higher and higher, directly approaching a value of 3. We call this the left-hand limit, and we denote it with a tiny minus sign next to the 2. But look at what happens if we shift our perspective and approach 2 from the right-hand side, meaning we only consider values of x greater than 2. Suddenly, we're tracking along a horizontal path at an altitude of exactly 1. So, as x approaches 2 from the right, our function value remains firmly at 1. We write this right-hand limit with a tiny plus sign next to the 2. This reveals a profound theorem in calculus. A regular two-sided limit can only exist if and only if both the left-hand limit and the right-hand limit exist and agree on the exact same value. Because 3 doesn't equal 1, our paths never meet. Therefore, we must conclude that the overall limit as x approaches 2 of g of x simply doesn't exist. So, we've seen that a limit can fail to exist because of a violent jump in the graph. But there is more. Let's consider a highly deceptive case that routinely traps students on exams. Let's look at a function f of x equals sine of pi over x as x approaches 0. If you attempt to evaluate this numerically by testing simple point, you might reach a very dangerous conclusion. For instance, if we test x equals 1, we get psi pi, which is 0. If we test x equals 0.1, which is 1 over 10, we get psi 10 pi, which is also equal to 0. If we plug in 0.01, we get psi 100 pi, which is again equal to 0. It seems entirely reasonable to guess that the limit is simply 0. But if we look beneath the surface, we see an infinite trap. As x gets closer to 0, the term pi over x blows up towards infinity at an accelerating rate. This means the sine wave is forced to cycle through its entire period between -1 and +1 infinitely many times as we approach the origin. The function is wild, oscillating with frantic energy, completely refusing to settle down to any single number. Because it never targets a stable value, the limit doesn't exist. This serves as a vital warning. Numerical guessing on a calculator can be a profound illusion. We need exact algebraic tools. So, how do we break through these indeterminate walls without relying on deceptive tables of values? We use analytical deconstruction. Let's walk through two classic strategies that show up on almost every high-level calculus paper. First, let's look at a method of rationalization when dealing with radical expressions. Suppose we're asked to find the limit as t approaches 0 of the fraction, the square root of t squared plus 9 minus 3, all divided by t squared. Direct substitution immediately hands us that familiar ghost, 0 over 0. To break this open, we introduce a brilliant algebraic tool. We multiply the numerator and the denominator by the conjugate of the expression on top. So, we multiply by the square root of t squared plus 9 plus 3. Watch how cleanly the algebra unpacks. The numerator becomes a difference of squares. The square root squared vanishes, leaving us with t squared plus 9 and then minus 3 squared, which is 9. The plus 9 and minus 9 cancel out completely, leaving just t squared on top. And because we're evaluating a limit where t approaches 0, we're explicitly stating that t is not equal to 0. Therefore, we can cancel t squared on top with the t squared on the bottom. This leaves us with a clean expression, 1 divided by the square root of t squared plus 9 plus 3. Now we can comfortably use direct substitution. Letting t equal 0 gives us 1 over the square root of 9 plus 3, which simplifies directly to 1 over 6. Now, let's consider a second incredibly elegant tool, the squeeze theorem. Suppose we want to evaluate a limit as x approaches 0 of x squared times sine of 1 over x. Earlier, we proved that the limit of sine 1 over x by itself fails to exist due to wild oscillation. So we cannot simply split this into a product of limits. Instead, we construct an analytical trap using basic trigonometry. We know with absolute certainty that the sine function, no matter how wild its argument, is always bounded between -1 and +1. Since x squared is the squared term, it is guaranteed to be greater than or equal to 0 for all real numbers, meaning we can multiply our entire inequality by x squared without flipping the direction of the size. This gives us -x squared is less than or equal to x squared times sine of 1 over x, less than or equal to x squared. Now look at the boundaries. As x approaches 0, the lower bound -x squared clearly goes to 0. At the same time, the upper bound x squared also goes to 0. Our target function is completely trapped in the middle, squeezed by two functions closing in on the exact same coordinate. Therefore, by squeeze theorem, the limit must equal 0. When you look at limits from this perspective, they stop being a series of arbitrary algebraic steps and become a highly disciplined study of trends and boundaries. If you want to master the rest of calculus with this level of analytical precision, make sure you hit follow. We break down complex topics almost every week, turning raw mathematical theory into concrete exam utility. Work through these steps yourself, look closely at the logic behind the algebra, and I'll see you in the next one. Bye.